So we did a lot of things with quadratic equations. Quadratic equations are those equations where the highest power is 2, right? So whenever you see an x squared as like the biggest thing in your equation, that's a quadratic equation. Okay. Talked a lot about different methods to solve these equations. Factoring, completing the square, square rooting. We also talked about the quadratic formula, which is kind of where we left off. And remember, the quadratic formula is a formula you have to memorize. There's a nifty song if you want to use it to help you memorize as well. And we did a little bit of work with this, and I think the quadratic formula is one of the easier ways to factor things because you literally just stick it in the formula, right? Did a few examples with it. Did an example where we had a rational expression where we had to use the quadratic formula to solve it as well. And I want to go through two other like weird things you can do with the quadratic formula. I think you'll see example 4, maybe something like this on your homework. So let me just go over how to use the quadratic formula to maybe solve some weird questions. So if we go to example 4, we're asked to factor this polynomial. It's a quadratic polynomial because the highest power is 2. And normally, if you wanted to factor something, you would use the factoring methods that we've used before. But these numbers are really, really big, right? And I really don't feel like multiplying 21 times 20, looking for things that multiply to that and add to -13. That seems a little bit weird, right? So why don't we use the quadratic formula on it, and maybe it'll give us some idea of what maybe the factors might be. Okay, so quadratic formula, remember we have A, we've got B, and we've got C, okay? Anyone want to remind me of the quadratic formula? Perfect. All right. A little too early to start singing it, right? All right, but we got it down, and that's all good. All right, let's plug it in. So we got B -13. So we got a -13. We've got a B squared, -13 squared, -4, 21, -20. All over 2 times 21. All right, now here's where my arithmetic skills are put to the test. I did this before class, but sometimes I'm not very good. So a negative is a +13. On the inside, I'm getting 169 plus 1680. Okay, and that's over 42. Okay. Okay, once we get that, I guess I can add the inside of the square root to get 1849 and keep everything the same. Okay. And if you go in your calculator and do the square root of 1849, I'm pretty sure we get 43. So it actually turns out to a nice number. 13 plus or minus 43 over 42. Okay. So this is a solution to my equation, okay? Let's get like the two different solutions, okay? So I'm gonna take the negative version, I'm gonna take the positive version, find the two numbers, right? So we've got 13 minus 43 over 42, and I'm getting minus 5 over 7, okay? And then we've got 13 plus 43 over 42. And I think that's getting me 4/3. So all I did is I found the positive and negative answer. Okay. So let's talk about what these numbers actually mean. Okay. Aren't these two answers the solution to my equation equaling 0, right? That's kind of what we would do if the question was like, what's the answers to 21x squared minus 13x minus 20 equals 0, right? Those would be the answers. Okay. So, you know what I'm going to do? I'm going to create an equivalent equation to this answer. And remember, equivalent equations have the same solutions, okay? Can we all agree that maybe this, x minus 5/7 times x minus 4/3 equals 0? Can we agree that those two equations have the same solution? The answers to this guy is 4/3 negative 5/7. The answer to this equation is also 4/3 and negative 5/7, right?
Why is the minus 4/3?
Because if I plug in 4/3 into here, right, into this guy, that's going to be 0, right? And then that would make the equation 0 equals 0, which is good, right? All right, and if I plugged in negative 5/7 in here, well, that would make the equation 0 as well. Okay, so these two are equivalent. I'll write that down too. Equivalent. Okay, so essentially I've taken my equation or my expression here and I factored it, right? I found another way to write it with the same answer. Ainsley? Oh, I'm sorry. Thank you so much. Should be plus. All right. Okay, so I've taken my equation. I've definitely factored it. So I guess x plus 5/7 times x minus 4/3. That is a factored version of my polynomial. Now it doesn't look like it, right? If I multiplied out this thing that I wrote here, do you really think I'm going to get 21x squared minus 13x minus 20? No, right? That's not gonna, well, that doesn't really work, right? Any ideas on how to make it maybe not have a fraction? Okay, let me rewrite the equivalent equation here. Okay, what if that equals 0? Well, if I have an equation, I can do the same thing on both sides. Okay, what can I multiply on both sides to maybe take out the denominators? Yeah, 7 and 3. 7's in the denominator, 3's in the denominator. I'm going to multiply by 7 and by 3 on both sides. Okay. All right, well, 7 times 3 is, God, I'm not thinking properly. Is it 21? Okay, perfect. All right, so, okay, how about, oh, wait, I don't want to do that. Sorry. Let's keep it as it is. Okay, how about I multiply the 7 to this one and the 3 to this one? Okay, I can't multiply both of them by both 7 because I would need 2 7s for that. So I'm going to multiply the 3 by the second expression, the 7 by the first expression. Okay, so on the left-hand side, I'll get 7x plus 5. The next term multiplied by 3 is 3x minus 4. And on the right hand, I have 0 as well. Now, all I've done is done the same thing to both sides of the equation. So this equation is also equivalent or has the same solutions as that one, right? And the second equation was equivalent to our first equation, which means this does have the same solutions as our first equation right here. Okay. So because of this, what I've done is I've actually set up an equation. It has the same solutions as setting the original question equal to 0. So they're equivalent, which means this is actually a factored version of our original polynomial. Okay. So we've gone and factored it. It looks like our equation or it looks like our original expression. If I multiply this out, I would get 21x squared minus 13x. Any questions on what I've done? I know it's a little complicated. It's basically using the quadratic formula and multiplying over the denominators, okay? If you have any questions after this on the homework, just let me know. We can work through a few more of these. All right. I'm going to show you one more thing you can do with the quadratic formula. I don't know if I put this on your homework, but let's just go through it just in case it's on there. I kind of forget what I put on the homework. Okay. This question looks sort of familiar. Looks like our solving equations, but it's telling us that, well, x has to be less than or equal to 3, okay? And it's that we don't have like you have an x and a y here, which is kind of weird, okay? Okay, let me just rewrite our equation here. Okay, we want to solve this for x, but we don't have the equation being equal to 0, right? I know this looks weird, but what I'm going to do is I'm just going to move everything to the right-hand side. And maybe there'll be a 0 when I do that, right? I'm going to subtract y on both sides. Okay, so we're left with 0 equals x squared minus 6x plus 5 minus y. Now I have a 0, which means I could use my quadratic formula, right? Okay. What's A here? 1, good. What's B? What's C? 5. Anything else? 5 minus y, right? Y is a variable, but if I plugged in a number like 1 or 2 or 3, it would be 5 minus 1, 5 minus 2, or 5 minus 3. 5 minus y in itself is a number, right? So my C is actually 5 minus y here, okay? Okay, we have a bunch of things. We can plug it into our quadratic formula again, right? So we've got x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, now we're here. Let's just kind of clean it up and see what we can do, okay? I can definitely, a negative is a positive 6. We've got negative 6 squared, which is 36. And 4 times 1 is 4. And then 2 times 1 is 2, right? Okay. All right, any ideas on what we can do now? We got some multiplication going on, right? Maybe I can distribute the 4, right? So why don't we do that? So I can take my 4 and move it into the 5 and the y. I just have to make sure to distribute the negative as well. So this becomes 6 plus or minus the square root of 36 minus 20 plus 4y over 2. Guess I can subtract the 36 into 20, right? 6 plus or minus the square root of, 16 plus 4y over 2. Okay. So we're here now. Okay. I'm going to do some funky things. I'm trying to decide if I put this on your homework or not. Is there something that looks like this on your homework? Does anyone remember? Let me do a little check. I'll show you how to do this, but just to be sure, let me go to website. I think this is a little hard, which is fine, but let's see. Let me do a little check here. So we've got 2. Okay, I don't think this is on your homework. All right. Well, let's continue doing it. I'll show you how I would do this, but if you feel overwhelmed right now, you don't have to know it. Okay. Okay. So I'm going to do something a little funky. Okay. And you might see this going on if you like go to calc and things like this. Okay. I'm noticing the 16 and the 4 have a 4 in common, right? So I'm going to take that out. Okay. So this becomes 6 plus or minus 4 times 16 take away 4 is 4. And 4y getting rid of 4 is y. Okay. Now, square roots are just like exponents. You can always kind of split them apart, okay? So why don't I take my 4 and my 4 plus y and kind of just split them apart? What's the square root of 4? 2, good. So this becomes 6 plus or minus 2 times the square root of 4 plus y over 2. Okay. Now I got a 6 and a 2 up top. They share something, right? So why don't I take out a 2 from the numerator? It doesn't really matter if there's a plus or minus, right? So 6 removing a 2 is a 3, right? Plus or minus 2 square root of 4 plus y divided by 2 is just the square root of 4 plus y. So I just factored out a 2 on top. Any ideas on what I can do now? Yeah, cancel out the 2's. I can cancel these out. So I guess I'm left with 3. Perfect. 3 plus or minus the square root of 4 plus y. Okay, so we got our answer, right? Now here's where things get a little tricky. Okay. I know it's already tricky and now I'm making it more tricky. Okay, if we go to the question, it's saying we need to solve for x, and we got our value of x, but it says that x has to be less than or equal to 3. Okay, so I'm going to remind myself, x has to be less than or equal to 3. Okay, let's write out our 2 answers and see if maybe one of them doesn't make sense. Okay, since I have a plus or minus, I have a 3 minus the square root of 4 plus y. And then I have a 3 plus the square root of 4 plus y. Okay. When I have a square root of something, is it ever going to be negative? No. Okay, so you're telling me that this square root of 4 plus y is something positive, right? Okay. Okay, so taking a look at the negative root, the 3 minus the square root of 4 plus y. If I take 3 and subtract off something positive, is that going to be less than 3 or bigger than 3? Less than 3. So this is less than 3. Okay. On the other hand, if I take 3 and add something positive, is that going to be bigger than 3 or less than 3? Bigger than 3. This is bigger than 3. Okay. Since my answer has to be less than 3, which one is my answer? The left or the right? The left one, right? So this guy here is my answer. The other one can't because it's bigger than 3, and my question says the answer is less than 3. So therefore, the left-hand side is my only answer to this question. Okay. Now, if you want to make a note to yourself, I'm not going to test you on this type of question. So No test / quiz. Okay, I also don't see under your homework, so I think it's a good example to go through, but don't kill yourself if you're studying for the test. Any questions on this example here? All right. I think that sums up the quadratic equations part of our notes. So I do want to start the next section, but we're not going to do too much with it. So I'm going to pass out the new set of guided notes. We'll do a little bit and then we'll get to the quiz review. All right, so we're moving on to our new set of guided notes on the complex numbers. Now, I think some of you have worked with these types of numbers or at least seen them before. Anyone like kind of remember what complex numbers are about? Anyone remember like what they look like? Okay. Another word for complex is imaginary. Is that ringing any bells now? Yeah, these are the numbers that look like the eyes, right? So whenever you see an eye, they stand for imaginary. Yeah. Starting to ring a bell now. So complex numbers are the same thing as imaginary numbers, which I don't really like that name. We'll talk about that later. But whenever you see an eye, that's kind of what we're dealing with. Okay. I think complex numbers seem really hard to understand if you don't take a step back and try to look at the numbers, all the numbers as a whole. Okay. And once you start realizing how numbers are made, complex numbers get a little bit easier to understand how they came about. Okay, so if we look to like the history of the beginning of numbers, like how numbers came about, they kind of came about in different ways by different societies, right? And they came about in different ways, but they all started with counting. Okay, so they all started with counting. You don't have to write this down. Okay, this was the context that all numbers, oh gosh, counting. Counting, okay, counting, there we go. Okay, they all came about in the same way. And it's a very simple concept, but it's really important and it's very evident in all the different things that we use even now. Okay, for example, Roman numerals, right? 1, 2, 3, right? Now, you don't really pay attention to it, but counting is prominent in even the things that we see normally, right? When we count things, we have symbols to represent, okay? So Roman numerals are have a representation of counting in their numbers. Even different languages, I think the Chinese alphabet, 1, 2, 3, okay, same sort of deal here. And even the numbers that we use now in English or the Roman numbers, it's not all that different, okay? I don't know if you've seen this before, but I think, let me see if I can get this right. We've got 1, 2, 3. Okay, so even in normal numbers, counting is kind of evident. We just kind of take it for granted because we're not used to seeing numbers written that way. Okay. Here's the problem. Very rapidly, numbers don't end here, right? We don't just have counting numbers. There's different types of numbers. And people haven't figured that out until kind of really recently in comparison to how long the world has been going on. And it's pretty obvious to see that natural numbers aren't the only thing that come about. And by trying to combine numbers together using algebra, we can figure out different types of numbers. And before we get to complex numbers, for example, if we had a pizza and we had, I don't know, I'll put an odd number of slices in here, okay? And we had 3 people, okay? It's pretty obvious that we can't divide an odd number, or I don't even know how many pizza slices there are, to 3 people, right? We're gonna get a fraction of pizzas left, right? Another way of thinking about this is, I think it's back when the Greeks were talking about math, they realized that, okay, we can have counting numbers like 3 and 7, okay, as the 2 sides of my triangle, but they realized that this number isn't like 3 and 7, and it's not even a fraction, it's something else, right? So they kind of realized by combining these numbers together, we're going to get new numbers that kind of appear, okay? Okay. So this whole history about the development of numbers comes across, or we start with counting numbers, right? And then we combine them together and we build new numbers like division, right? We got fractions. And we also have square roots that come about. The same way these guys come about is how these imaginary numbers come about. Okay, so the way I'm going to explain this is we're going to start by building our language to describe all these different types of numbers, and then we're going to see how the complex numbers kind of arise out of these numbers as well. Okay, so let's just take a step back. Let's start with a simple algebraic equation. Okay, how about x minus 5 equals 0? What's my solution to that? X equals 5, right? Okay. And we're still in the realm of the counting numbers, right? 5, we can count to 5. And this is an example of the very beginning of how numbers were formed. This is an example of a natural number. And we use the symbol n to kind of denote this whole set of counting numbers, like 1, 2, 3. These are all examples of natural numbers for this big. Okay. Now, numbers don't stop there. We have, if we just slightly modify this equation, we bring rise to other types of numbers. Let me give you an equation, x plus 2 equals 0. Okay. I just kind of modified my algebra, how I arrange these numbers, how I'm combining them. What's my solution now? X equals -2. Okay. And we haven't talked about negative numbers yet. We talked about natural numbers, the counting numbers. Now we realize by combining these numbers together, if I set up an equation, now I'm getting negative numbers, okay? Now negative numbers bring rise to a different type of number. It's denoted by a z, which is kind of weird because they represent the integers. Okay. Anyone know why it's a z? All right. I think integers were developed primarily by the Germans, and they called integers Zahlen. So that's why it's a z. Okay. Okay. So we talked about taking an x, adding and subtracting numbers to it. Well, let me modify this equation even more. Let's do 2x minus 1 equals 0. Okay. Now I've added multiplication to the equation, right? What's my solution now? 1/2, right? So now I'm introducing fractions to my numbers, right? So we started with integers, or no, we started with natural numbers, which are the counting numbers. Combine stuff to get integers. Now we're dealing with fractions. Anyone want to guess what these guys are called? We actually talked about this word before. It starts with R. Rational numbers. Rational. And we use the symbol Q to denote that. Anyone want to guess why it's a Q? Well, when we divide stuff, we have a quotient, right? That's why we have a Q to represent the rational numbers. Okay. All right, so we have a pretty good equation here. Let me modify it even more, okay? So instead of having an x, why don't I start with an x squared? X squared minus 5 equals 0. If I solve this, what would I get? Yeah, square root of 5, but what am I forgetting? Plus or minus sign, right? Okay. So this is an example of something that the Greeks found out. This is where that hypotenuse of a triangle kind of developed. It's a number, but they weren't sure what it was. They created this thing called the square root. Okay. So square roots combined with all the other numbers are an example of this set called the real numbers. So integers, negative numbers, 0, fractions, square roots, they all represent things that are called the real numbers. If you've noticed when we've been doing problems before and we got something that didn't have a solution, we would say no real solutions. Okay? And this is because this is where we stopped with our numbers. We didn't think about any other type of number. Okay? All right, I'm going to modify our equation one more time. I'm going to have an x squared. Why don't we say x squared plus 1 equals 0? Okay. What's my solution to this equation? Yeah, x equals plus or minus the square root of negative 1. Yeah. And here's where we got the no real solution because we didn't have any language to describe what the square root of a negative number is. Okay. And this is where that term I comes from. Okay. I is the square root of -1, and it comes across by combining real numbers to get different types of solutions. Okay. And we call these the complex numbers. Okay. So complex numbers aren't that hard to understand. All they are a combination of real numbers to get the square root of a negative number. So whenever we're talking about square root of a negative number, that's where we're talking about the complex numbers. All right. Any questions? All right. Next class, we will talk about how to combine these together. Let me just take a look at our quiz review. Good. Okay. All right. I think it's about time for a quiz review. So let me just tell everyone on Zoom where it is. If you go to home, scroll down, click on quiz 2 review. This is what we're doing.